we are going to talk today about vector spaces. So I hope that this will be kind of, well, before I get rolling too much, any questions kind of hanging over your heads? Well, so we're going to talk about vector spaces, and in a certain sense, we've already talked about this. I didn't really call them, well, I didn't call them vector spaces, but what we were talking about before was Rn, right? Euclidean space, right? So we talked about vectors that had n entries that had real numbers in it, right? Column vector. Well, we're going to generalize this now to vector spaces, and we're going to show, I'm going to give you a bunch of examples. I'm going to show you what a vector space is. But really, this is all very intimately related to stuff before. And in a certain sense of the word, if you get deeper into the math, really, this is absolutely no different at all than what we've done before, which is good news, right? So let me first of all tell you what a vector space is. And when I tell you generally what this is, you should keep the picture of the vector spaces we've done, Rn, in the back of your head. When I talk about vector spaces in this class, it will almost always be real vector spaces. So vector spaces do what they did in Rn. You've got two things going on. You've got something called a vector and something called a scalar, which is something you can multiply with. My scalar will come from R, but if you want to get more general than that, they can come from, scalars can come from any field, they can come from rational numbers, complex numbers, etc. Okay, I haven't told you what so far. Let's see the little circular. A vector space is just a non-empty. This is the lawyers making me avoid doing something silly by having nothing there at all. There's at least one vector. I want to call these objects vectors, and these vectors can be added or subtracted, actually, and multiplied. For our purposes, elements are. So here are the rules for what the vectors being added and multiplied by scale. This is in place. Number one, say for all U, V, W, and B are vector space. And A, B in real numbers, we have the following rules. And one of these rules are just to make sure that this is a nice place to play. A vector space is a playground. It's used all the time, and some of you may have already used it in physics and mechanics, dynamics, this kind of thing. We want our playground to be a nice, useful, and healthy place to play. Number one, add two vectors, it's still a vector, still in the vector space. And when I multiply a vector times a constant, it's still in the vector. So that's the first rule. Adding and multiplying by a constant, you're still in the playground. This is a nice rule to have. What it says is it doesn't matter which order you add vectors in, you get the same answer. All right, that's good to know. Number 3. By the way, just what kind of cultural literacy here. Anybody know what this property is called? Right, it's called the associative property, and we're crying out loud, certainly won't back, right? Otherwise, it's just death on a hot plate. So we want this. These are kind of common sense rules here. 4, there is a vector 0 in V. So there is a magic vector 0 called 0 vector in V, such that when you take any vector and you add it to the 0 vector, it returns the original vector. So there's a magic 0 vector that when added to anything, it doesn't change. For all V in the vector space, there is a magic vector, which I will call negative V, such that V plus negative V equals 0. That just means that every vector has a minus sign. So given any vector, you can find some other magic vector that you added up to, and it gives you this 0 vector that I was promised earlier. Okay, like I said, we've got two things going on here. We've got you can add vectors and you can multiply vectors by numbers, right? Add vector, still a vector, multiply by a number, still a vector. Now that I've covered the basis for adding stuff up, I want my scalar multiplication and my addition of the vectors to play nicely together. I want them to not do anything weird, right? So here's what our rules for playing together is. When I take the vector u plus v and add it to a, what do you suppose playing nicely means? What do you hope that is? Right, I hope that this kind of you can distribute it out. So I'm going to make that a rule. And not only that, I want to distribute across the constant as well. When I take a plus b times the vector, this should be a vector plus b single. I want that to happen. Yes.
Can you create a vector space where that isn't true?
What's that?
Can you create a vector space where that isn't true?
No, by definition, because this is the definition of vector space. Can you create a space where that doesn't hold? Yes, but you know, it would really suck. So, you know, why would you ever want to use it, right? Because the whole point of making these things here, the whole point of having this play nicely together is so this is actually useful. And this is the kind of thing that you kind of physically hope that this would happen too, if you've ever played vectors in mechanical classes. But yes, there are people that study more general structures where, I mean, even some structures where this doesn't hold, which is really bad, right? So you can generalize on those things. But here we're going to concentrate on nice now. Anyway. So you've got something like an associativity of your scalar multiplication. And here's one last rule. And you might think about, well, we put this in here. There is a real number called one, and when you multiply any real number by one, you get the same thing. It should work the same on vectors. That is to say, when you take one and you multiply it by any vector, it should return like. Okay. Any questions? Oh, let me make a note here. I'll do it over the math problem. I have something that I need to do in the 10 to 11 o'clock block, so I need to be out of the office. If this is going to wreck your life, come talk to me after class. Think of something else. Okay, here's some consequences. If you have what do you suppose? What do you suppose that should happen if you multiply any vector in the world times the number 0? What do you expect to come out of that? Zero vector, right? This is not one of our rules. This is a consequence of our rules. Can anybody see what rule this comes from? There are probably several ways you can call it. Did anybody see why this follows?
Number 6. It's distributed.
I'm going to use some of that. Actually, I'm going to use several of them, but I'm going to start here. So why is this true? Why was it? Correct. How that helps. What do you suppose this is?
0.
Well, no, just the negative e by itself.
Should be with all the
Actually, we should probably clear that up here. Negative b is actually negative 1 times b. Now, if you pull b down by rule, actually, this one, number 7, right? This is 1 plus negative 1 times b. Everybody okay with that? And I don't know what's 1 plus negative 1? 0. So it's 0, b, 0. Now, the big question is, how did I make this step? So see if you can show, so kind of an exercise, if you can show, fun, that negative b is actually equal to negative 1 times. If you use these rules, you should be able to show this. Any questions? Here's another one. Here's another consequence of all this. Here's another consequence. If you take the zero vector and you multiply it by what do you suppose I get here? The zero vector, just like I did before. With ordinary movement. Right? This is another consequence that follows from all the rules that I get. See if you can figure out why that's. Okay. So, let me give you one more definition. So what I've given you so far is this long list, right? There were like 9 things on the list. This is what it takes to be a vector space, right? Most of these, like the associative law, the commutative law, U plus V equals V plus U, and things like that, are things that you can kind of hope for with regard to common sense, I think. The key part is when you multiply a vector by a scalar, it's still in vector space. And when you add two vectors, it's still in vector space. That's kind of sort of the central theme of this. Let me give you one more definition, and then I'm going to basically, I'm going to do examples of the fluid phase, because I think I'm familiar with all this. So now I formally know what a vector space is. An example of a vector space would be Rn, right? N-dimensional vectors. We've done that. What happens when you take 2 n-dimensional vectors and add them up? You get an n-dimensional vector. What happens when you multiply an n-dimensional vector by a scalar? N-dimensional vector. And it satisfies all those crazy rules, right? Does anybody remember what it meant to be a subspace of Rn? I think we had like basically 3 things we had to say. Anybody remember what they were? Yeah. Okay. Okay, so let me take this part one by one. So the first thing is you got to have the zero vector in the subspace, right? Okay, that was one thing that we needed. And there were 2 others. Anybody remember what they were? Yeah.
Closed under scalar multiplication and addition.
Closed under scalar multiplication and addition. So what does that mean? That means if I have 2 things in the little subspace, 2 vectors, V and W, when I add them together, it's a new vector. It's still in the subspace, right? And if I took a vector that's in the subspace, I multiply by a scalar, it's still in the subspace, right? The rules for subspaces in general, exactly the same. Now, subspace W of the vector space. So here we have the parent vector space V, and here we have the little baby W. It's a subset, right? So to be a subspace, it has to be a subset, and it has to satisfy the following 3 things. Number 1, the zero vector is, so whatever the subspace is, zero vector. Number 2, if W1 and W2 are in W, and so is W1. That's the second. If you have 2 vectors in the subspace, so is its sum. Yes.
For a subspace W to be a subspace, doesn't it also have to be a subset by default?
Yes. Any subspace has to be a subset. If W is a W and C is a real number, then CW is also. That's it. If you look back to what we had before, these are the exact same rules for a subspace Rn, right? A subspace has to be the zero vector. It's going to be closed under addition of vectors and multiplication by scale. So let's do a lot of examples here. Consider the collection of all infinite sequences. So this is like back in Calc 2, right? Y'all remember when you studied sequences there? And what was the big question you always asked about sequences? What's that? Right, that was a big question you asked. Does the sequence converge or does it not, right? Y'all remember that? Maybe you're still in therapy over it or whatever, but yeah, it's somewhere back there. You like look at these sequences and such, right? Now, I claim that this is actually a vector space. But before I can tell you it's vector space, I'm gonna have to tell you what my rules are. I gotta tell you how to add them, and I gotta tell you how to multiply by scale. Okay? In fact, maybe you can help. So we'll call this vector space, we'll call this S sequences. Now, suppose I have two vectors, right? So my vector is going to be, actually, I'm going to flip around black and face. So suppose AN and BN are in S, and C is in R. Okay, so these two things, AN and BN, these sequences are, they're going to be what I want to call my vectors. And C is just a number. Now, I got to tell you how to add these things and multiply by scale. Now, anybody want to guess at what's the intelligent way to do this? And remember my adding. This is a math class. If it ain't easy, don't do it. All right? What is the most logical way that you can think of I need to add two vectors and get a new vector, right? That's what has to happen. So I need to get a new sequence out of this. Add this to this, and I need to somehow have it barf out a new sequence for me. What's the easiest way you can think of? There you go. Just add them coordinate wise. So input vector, vector, output new vector, right? So I've already got that. When I add two vectors, I get a new vector. Because that new thing there on the right side of that equation is vector, right? Because it's an infinite sequence. Am I okay with it? Okay, let me ask you this. What do you suppose it means to multiply, or what should I define it to be? How should I multiply that scalar times a vector? And remember, my output's got to be a new vector, in this case, sequence. What's the easiest thing that I can do? Very good. That's exactly what it is. Now, the way I've set this up, I've already satisfied the first rule, because the first rule said that when I add two vectors, I need to get a vector. And that's what I've done up there. Two vectors, two sequences, get a new sequence. Number two, I've got to multiply, being able to multiply a vector times a constant, get a new sequence. There you go. Got that as well. What about the other rules? And I'm going to go through these pretty quick. Does it matter what order you add these up in? No, it doesn't, right? Because AN plus BN can be, it doesn't matter. Is it associative? Sure it is, because the real numbers in the coordinates are associative addition, right? Let me ask you this. What do you suppose, who plays the role of the zero vector here? What is the sequence? Look at that rule. What can I add to any sequence and it leaves it alone? Right, the sequence consisting of all zeros, right? Just all zeros. What do you suppose? The role of the negative vector is that, because if I take this vector and add it to the vector an, I'll get the zero vector, right? Now, what I have now is rules 6, 7, 8, 9. Notice that when I multiply this sequence by 1, I get the same one back, right? So that last rule will work. And the other rules are easy to verify too. So this is vector space. Everybody open? I want to continue with this example here. Let me ask you all this. Did anybody see a subspace? Now I'm waiting for the smart aleck answer. Anybody got a smart aleck answer for me? Okay, very good, right? So let me kind of throw this in the middle of the example. Recall for any vector space, whatever it is, B, the zero vector and B are subspaces. In a very silly sense, right? Well, let's go back to our vector space S. Can anybody give me a subspace of this that's not zero and not the whole thing? Yeah.
Same terms, but we don't have the finite number instead of.
Huh. So what you're really saying is all the terms are bounded, right? So given any one of these right here, there's an upper bound to how big the terms. Yes, actually, I think that'll work, because what happens if all the terms in the sequence are bounded by some absolute value, right? Maybe they're always between plus n and minus n. What happens if you have two vectors or two sequences and all the terms are between two numbers, right? Suppose the first one's between n and minus n, and the second between n and minus n. Then when you add them up, it'll be between n plus m and minus n, right? So when it adds up, it's still in there. If you have a sequence and it's between n and negative n, what happens if you multiply that by a constant? That's right, so it's still bounded. And is the zero vector bounded? Right, that was bounded too. Actually, that's a really good example. That's a really good example. So that's one subspace where every term is always, where all the terms are bounded by some fixed number. Here's another one. Well, what about the collection of convergence sequences? Right. So what happens here? Is the sequence 0, 0, 0? This is convergent, it converges to 0, right? Okay, good. So you got the 0 vector. What happens if we have two convergent sequences? Suppose we have two convergent sequences like this. Limit as n goes to infinity of an is k, and limit as n goes to infinity of bn is n. Is the sum of these convergent? Look at this sequence here. Does that converge? What is the limit? As n goes to infinity of an plus b, given this. So if if my vector is convergent, then its sum is convergent. So when I add two of these, it's still in there. So we've already got two of the things. We've got 0, we've got sums. What is the limit of c times a? This is actually pull c out, ck. So that's a subspace as well. Yes.
So to be convergent, what if the limit as it approaches infinity of a sub n have to equal to 0 instead of k?
You're thinking of series, right? This is just sequences, right? You're thinking of the theorem that says if you add them up, then what you're adding up has to go to 0, right? But for example, if you look at the sequence 1, 1, 1, 1, 1, 1, 1, 1, 1, you can't add that up to something finite, but the sequence is converging to 1, right? Sequence itself. So he gave a good example that one. So I'm gonna give you credit for yours too. B was a subspace, and so was my convergent ones too. Are they the same?
No, because B could be something that's like comparing,
Okay, that's right.
oscillating between the two numbers, and it's still bounded.
You actually can compare them, right? The master vector space is S, all sequences, right? His, the one that he gave is bigger than mine, because his has, for example, that is a vector that is in his space, because every term in there is between, I don't know, make it up, -2 and 2. Everybody agree with me? And actually, I should have, but yeah. But this one is not in mine. Is that a convergent sequence? No, it goes back and forth. They can't make up its mind on the limit, right? So, in fact, you can show that everything in mine is actually in his, because if it's convergent, it must be bounded. Okay, let's look at any questions on that. Yes.
Was B just not the S? Because like you could just adaptively change the size of like K Just be the highest number.
No, I'll give you an example. Consider the sequence 1, 2, 3, 4, 5, 6, 7. Right. There are certainly sequences that are in S that are not in. Okay, let me look at another one. Example. I'm gonna go from big to small. And this will have kind of a calculus feel to it, only we're going even further back in time because we're going to look at something that's more like even sort of more in count one. This is actually a huge, very general vector space. Let me tell you how I'm going to add two functions. Right? This is just a collection of all F from R to R that are functions. They don't have to be anything nice like you've seen, any function that you like. And I am going to find F and G, F, C. I'm going to find F plus G of X is Fx plus G. And in fact, this is just the way you add functions in calculus. It's just a pointwise addition, right? Like if you wanted to add up the function sine and cosine, it's just sine x plus cosine x, right? If you wanted to add up the function e to the x and tangent x, it would be e to the x plus tangent x. That's it. Right? When I add two functions like this, I get a function. And a multiplication just like that, right? So in other words, the function 2 times sine x is just twice sine x, like that. This is a vector space, right? By the way, anybody want to guess what the zero vector here is?
Is it just the point zero? Is it all-
That's the spirit. It has to be a function, right? To live in here, it has to be a function. So such that f of x is 0 for all x. So if you were to graph it, it would just be the, the x-axis, just a horizontal line, right? This is a function that you added to any function that doesn't change it, right? Right. The order of functions by my rule, it doesn't matter what order you have them in, it's the same. It's associative addition because the output's always in the real numbers. And this satisfies vector space. Everybody kind of okay with that? This is a massive vector space. Anybody think of a subspace bed other than itself and just the zero function? Here's one from calculus that you look at. Let's see the set of F and R such that F is continuous. This is actually a subspace. Now I'm gonna appeal to your knowledge, hopefully semi-profound calculus. Is the zero function continuous? You can certainly draw that without picking up your pencil, right? So notice that zero vector is continuous. And here's a calculus theorem. Y'all remember this was actually quite fairly early on when you took calculus. What happens when you add continuous functions? What do you get? It's still continuous. Do y'all remember that theorem? Maybe if you take whatever you like, e to the x and sine x, those are both continuous functions. When you add them up, you get a new continuous function, right? So here, F and G are continuous. So is F plus G. And what happens if you scale a continuous function? What happens if you have a continuous function F and you multiply by 2 or 7 or C? What happens? Still continuous. Now, they don't tell you this in calculus, but one of the reasons that continuous functions are important is they form a vector space. Still very big. So this is the backdash, the big one in my example. This is a subspace. Can anybody think of a subspace of the continuous functions that you might have seen in calculus? What's the big thing you did in Calc 1? You did it until I wanted to vomit. You took derivatives all over the place, right? What kind of function is it that you can take a derivative of? Can you always take a derivative of a continuous function? Yeah, there's some problems, aren't there? Right? If you look at the absolute value function, which I've drawn very badly, this one's not differentiable over there, right? Because it doesn't have a problem right here at the origin. But it's continuous up there, right? Because I draw it up in the chart. Well, yes. Actually, that's really fancy terminology. Yeah, depending on what the author is, sometimes consider that. Sometimes smooth means the first derivative is also continuous, but I'm going to use a more primitive word. D equals set of F from R to R, such that F is differential. That is to say, F prime of X exists for all. Notice that 0 is differentiable. Right? In fact, it's its own derivative, right? The derivative of 0 function is 0 function, right? If F prime and G prime exist, then F plus G prime equals F prime plus G prime. So F plus G is in D as well. And let me ask you this, what happens if you take the derivative of a constant times a function? The constant pulls out, doesn't it? Right? And so CF is in D. This is a differentiable function as well. So now we've got a smaller subspace of this one. Continuous function's big, differentiable function's a little bit smaller, because in fact, this function right here is in C, but not in D. Everybody okay? And we can go smaller than that, right? So let me be explicit about this. Okay. Y'all remember polynomials, right? Things like 2 and x and 4 plus x 17 plus x to the 29 plus radical 2x to the 30. Right? These are polynomials. You can think of these polynomials as functions, right? In fact, probably in calculus, what's one of the things that you found out about polynomials? They're continuous and they're differential. Right? So these polynomials actually are a subset of the differentiable functions. And it's not all the different. Can somebody name me a differentiable function that is not a polynomial? Which one? Right. Let
Or
me
not
see.
any of them.
Right. Very good. Well, let's stick to the ones that are defined everywhere. Yes, like sine x, cosine x, e to the x, 1/1 plus x squared. That's another example of something that's not a polynomial, but is in fact differentiable everywhere, right? These things are differentiable everywhere, and this is subspace because, let me ask you this, the zero function is also a polynomial because we define the zero polynomial to be just the zero function. Okay. What happens if I add two polynomials? I get another polynomial, right? What happens if I multiply a polynomial times a number? What do I get? A polynomial perhaps on steroids, but a polynomial nonetheless, right? So this is actually a subspace of the differentiable function. And you can go small. This is a very common thing to see a lot. And actually, this is going to be p of x. These are all polynomials such that the degree of p of x is no more than n, or p of x. This last one is even smaller than polynomials, because polynomials can get as big as you want, right? They can't go on forever, but you can have a polynomial degree 8675309. Just take x to the 8675309, and there you have it, right? Polynomials can have a degree as large as you want. What's p in x? What I'm doing is I'm just making sure that the polynomials are never too big with respect to the degree. So for example, P3x is a set of all polynomials like this. Oops, 3, 3, A0, A1, A2, 3 are all polynomials. So all polynomials like that. What happens when I add two polynomials that look like that? It's another polynomial. I mean, there's no way that I'm adding two polynomials to degree 3 and getting an x to the 4th term, right? That's not happening because I'm only allowed to add it. And what happens if I multiply a polynomial like that times a number c? Is it ever going to get to be a bigger degree? No. Right, it'll never get to be bigger. It might go to 0 if I multiply by 0, but that's okay as well. By the way, let me give you all kind of a little parting shot here. So I encourage you all to like look at some examples. Here's some other spaces. Solutions to differential equations, solutions to certain linear differential equations, right? If you have, and it doesn't matter if you've had differential equations or not, you don't need to show this. Show that every solution to this, if you consider all possible solutions, and let me point out, 0 is a solution to this, isn't it? Right, because you get 0 here, the second derivative of 0 is still 0, it balances this equation. If you look at the set of all solutions to this forms a vector space. If you look at the collection of all n by n matrices with scalar multiplication, that forms a vector space. So take a look at some of these examples. And let me point out also, this vector space right here, P3, is basically the same thing as R total. And we'll see that in a minute. Okay, any questions? Any questions? Well, stop by the math club if you're interested in it. Otherwise, you all have a good weekend. I've set your next quiz, so it'll be due on Tuesday. Don't forget you got one.